welcome to NS Academy. So today we are going to look at this summation. Summation n equals to 1 to infinity 4 to the power n upon n square into binomial coefficient of 2n c n. Now you have read the title and this is indeed arguably one of the hardest sums on YouTube present. But the sum basically consists of elements that have been already taught in high school only. So you know all of these symbols and formulas and you have applied them up to your class 12, right? So you know how the sigma symbol works, you know what the binomial coefficient is, you know n squared, you know 4 to the power n, you know everything. But the problem here is that we do not really have a way to approach this if we do not use these extensive methods that I'm going to show you. So the complexity of this integral is so high. Like if I were to rate it, I would rate it a 9 out of 10 minimum. So we will see how to solve this, obviously. But in the process of doing so, you're going to learn a lot of different kinds of techniques that you can use to solve infinite sums, how to use integrations inside sums, and how to evaluate binomial coefficient sums of any kind almost. So this is one of the methods that we are going to share now. Okay, so first let's name our summation as S, and S is equal to n equals to 1 to infinity 4 to the power n upon n square 2n c n. Okay. So in general, the sum looks like this. So it has powers of 4 here. So it starts like 4 to the power 1, 1 square, 2c1, right? And then it goes like 4 squared by 2 squared. And then you have like 4c2. And it goes on like this. But this is not reminiscent of, let's say, AP or GP or HP or any other sequence that you might have learned, right? Because you can check that you have the general term here. This is if this is Tn, you can check that Tn plus 1 minus Tn, this is not constant first of all, and neither is Tn plus 1 by Tn. None of these are constant and they all depend on n, and they do not depend really, like let's say the first order, second order, third order arithmetic differences. Even that doesn't fit in here because we have a binomial coefficient which grows exponentially. So if you have heard of Stirling's approximation, you would know that a binomial coefficient grows exponentially, and that is why this infinite series right here cannot be handled by any of the aforementioned methods. So what we are going to do instead is this. We're going to try and introduce some different way for the binomial coefficient to represent itself rather than 2ncn. So what is 2ncn? 2ncn is simply 2n factorial by n factorial into n factorial, correct? Okay, but we are going to introduce, first of all, the gamma function. Gamma of n is defined as 0 to infinity e to the power minus x, x to the power n minus 1 dx. This is called gamma of n. And let us right now define it for n greater than equal to 1 so that we have ease at hand. So we are not really trying to define all the fractional values of gamma right now. Let's just consider that n is a positive integer and n is greater than equal to 1. For n greater than equal to 1, we can show that this quantity here is equal to n minus 1 factorial. So this is what we have here. This is called the gamma function. We will know more about it in a separate video probably, and a lot of integrations and summations can be solved using this solely. And a version of the gamma function, an extended version you might say, is called the beta function, beta of a comma b, which can be represented in terms of the gamma function. So what is the beta function? The beta function is this: 0 to 1 x to the power a minus 1 into 1 minus x whole to the power b minus 1. Again, for the sake of simplicity, consider a and b are positive integers. Now this integral is called beta a comma b. Beta has two parameters, and in terms of the gamma function, it is represented as gamma a, gamma b by gamma of a plus b. So you can also write their factorial notation. Since gamma of a is a minus 1 factorial, gamma of b is b minus 1 factorial, you can write them in terms of factorials as well. Okay, let's now try and see if we can write the central binomial coefficient, that is 2ncn, in terms of the beta function. So 2ncn is 2n factorial divided by n factorial whole squared, correct? Now 2n factorial in terms of the gamma function should be gamma of 2n plus 1. and n factorial should be gamma of n plus 1, right? And we have another copy of it. Now this somehow basically matches this, but in the reciprocal form, right? We must have this in the denominator. But then again, we have gamma of a plus b in the denominator and gamma a gamma b in the numerator. That is when it becomes a beta function. But here you can see our a's and b's add up to 2n plus 2, which is not the case here. But we can change that easily, because what we can do is we can introduce a 2n plus 1 in the numerator and the denominator, so that 2n plus 1 into, and you know gamma of 2n plus 1 is basically 2n factorial, right? Divided by gamma of n plus 1 into gamma of n plus 1. Now 2n plus 1 into 2n factorial in the numerator, this turns to 2n plus 1 factorial. So we have 1 by 2n plus 1 into gamma of, and now it becomes gamma of 2n plus 2 divided by gamma of 2n, n plus 1, right? Into gamma of n plus 1. And now if you write it in the denominator, it becomes 1 by 2n plus 1 into 1 by gamma of n plus 1 into gamma of n plus 1 divided by gamma of 2n plus 2. And now this represents the beta function. So therefore, 2ncn can be written as 1 by 2n plus 1 into beta of n plus 1 comma n plus 1. You can check that this is the definition of beta function for the values of n plus 1 and n plus 1 in terms of a and b. Okay. So what are we basically going to achieve by writing this? What I want to do is I want to represent our whole summation as, which was written as n equals to 1 to infinity 4 to the power n upon n square into 2ncn. I'm trying to represent this 1 by 2ncn in terms of an integration, so that we can get rid of the factor which is obviously bothering us the most. This binomial coefficient is something that is bothering us the most, right? So let's try and do that. N equals to 1 to infinity 4 to the power n upon n square. And now 1 by 2ncn from here can be written like 2n plus 1 into beta of n plus 1 comma n plus 1, correct? Then what we can do is we can write n equals to 1 to infinity 4 to the power n upon n square, and we would write the 2n plus 1 as it is. And now beta of n plus 1 comma n plus 1, according to the definition of integral representation of the beta function, we can write this at 0 to 1 x to the power n plus 1 minus 1, which is a here, into 1 minus x whole to the power n plus 1 minus 1 dx. Okay, this might be a little too much, but bear with me. The steps are hard, the functions are new, I can understand that, but still, this is going to be easier when we get through this part, because right now what we are doing is we are defining two new functions, gamma and beta, and then trying to manipulate them. And it's understandable if you do not know the gamma and beta functions, this is going to be a hard one. But assume that you know them, assume that they act as some standard results, and then you can see how this integral representation has simplified our problem. Okay, now let's write this like this: n equals to 1 to infinity 4 to the power n into 2n plus 1 upon n squared. And then we have the integral inside, which is x to the power n into 1 minus x whole to the power n, which we can write together like this. Okay, okay. Now what we are going to do is we are going to interchange the summation and integral. Because this is a sum of infinitely many integrals, we are going to write this as an integration of an infinite sum, which is valid here because this sum converges and all the terms are positive. And also there is a bound on x here. Okay, so what we can do right now is 0 to 1, n equals to 1 to infinity. And notice what I'm going to do is I'm going to introduce this 4 to the power n also inside this term, because all of these are multiplied, right? So I'm just simply going to introduce this inside this, because this is a constant and constants can be introduced inside the integration, which would make it something like this: 2n plus 1 by n square. Inside, multiply 4 with everything, you get 4x minus 4x square whole to the power n dx. So this is the infinite sum you have inside. Okay. Now what I'm going to do is I'm going to define a new function gy for simplification. And let this function be defined as an infinite sum. This is also called a generating function of 2n plus 1 by n square and y to the power n for some suitable value of y for which it converges, preferably less than 1, mod y less than 1. Okay, so this we can evaluate. Let's see how. N equals to 1 to infinity. Now, first do the distributive law, and you see that you get 2 by n plus 1 by n square y to the power n, and n equals to 1 to infinity. The first sum is 2 by n y to the power n. This converges, and this is the Taylor series of minus ln of 1 minus y because mod y less than 1. And the next part also converges, which has a special name in mathematical literature, which I'm going to introduce in a bit. Okay, so the first part, how do we do this? You have to remember the expansion of log of 1 minus x is given by minus x square by 2. This is something that you use in limits, or you should use in limits if you don't already. Minus x cubed by 3 and so on. This in summation notation is simply written as n equals to 1 to infinity x to the power n by n. Notice n equals to 1 to infinity y to the power n by n is the same thing, and therefore you can write this as minus 2 times ln of 1 minus y. This next term, this is n equals to 1 to infinity y to the power n by n square. We are going to write it in a special way. Let's write it li suffix 2 of y. This is called a dilogarithm function. This is called a dilogarithm function. So what is a dilogarithm function? So li2 of x is defined as the integral minus 0 to x ln of 1 minus x by x dx. So simply, the definition of dilogarithm is this integral. For different values of x, you put different values of x in the upper limit. And then whatever area you get into this curve, that is called the dilogarithm, right? Okay, so that is the basic definition of dilogarithm. Now, it is also defined in an infinite series as follows: n equals to 1 to infinity, x to the power n by n square. So this both are the definitions of dilogarithm, and this infinite series can be obtained from this integral as well and vice versa. Okay, so what we were doing, we were finding gy, which we have found as minus 2 ln of 1 minus y plus li2y. Notice the function inside the integral of inside the summation, this thing is basically nothing but g of 4x minus x 4x square, which is why we were evaluating gy in the first place. So our summation s simply becomes this: summation equals to 0 to 1, and then there was g of 4x minus x square, g of 4x minus 4x square dx. So we evaluated that this function is equal to, let's see what, it was equal to minus 2 ln of 1 minus y plus li2y, right? So we would write this as li2, that is dilogarithm of 4x minus 4x squared dx minus 2 times 0 to 1 ln of 1 minus 4x plus 4x squared dx. That seems cool. Okay. Okay. So we will try and evaluate this separately. Let this be I. Now, this is a easier integral, so you can simply write the inside one as 2x minus 1 whole square and then take the 2 outside. So you can write this as minus 4, 0 to 1 ln of mod of 2x minus 1 dx, and then separate it into intervals like 0 to half and half to 1 and evaluate this. This should come out as minus 1. And what you should get is I plus 4 as this. Now, it is also important to see that this integral cannot be evaluated directly. If you're just simply taking the 2 out and then evaluating it, answer would be wrong, because you see ln of mod of 2x minus 1 is there for a reason. From 0 to half it should be 1 minus 2x, right? Okay, now what remains is to find this integral I, which is going to be another challenge again, but let's try it. 0 to 1 dilogarithm of 4x minus 4x square dx. Okay, so we are trying to find this integral. First, let's make a couple of substitutions because you see this is reminiscent of x equals to sine theta. But we'll do one better. We'll write x equals to sine square theta. The reason would be pretty clear to you in a moment. So if you find out dx, it should be 2 sine theta cos theta, which is nothing but sine 2 theta d theta, right? Our integral turns, the limits become 0 and sine and you want to find out the value of theta. So for x equals to 1, theta should be pi by 2, right? Now we have Li 2 and inside we will get 4x whole into 1 minus x, which is 4 sine square theta whole into 1 minus sine square theta, which is nothing but cos square theta. And in dx we have sine 2 theta d theta. Okay, now this can be written as I equals to 0 to pi by 2 Li2 of, now this is again 2 sine theta cos theta whole square, which is nothing but sine square of 2 theta into sine 2 theta d theta. Write sine square 2 theta as 1 minus cos square theta, 1 minus cos square 2 theta actually, 1 minus cos square of 2 theta into sine 2 theta d theta. And the reason being I want to again substitute for cos 2 theta. So let t equals to cos of 2 theta. And in this way what you get is dt equals to minus 2 sine 2 theta d theta, correct? Therefore, I should be equals to, now the limits, let's calculate the limits first. So for theta equals to 0, cos 2 theta would be cos 0, which is 1. And for theta equals to pi by 2, we have t equals to cos of pi, which is minus 1. And inside we should have Li2 of 1 minus t squared multiplied by sine 2 theta d theta is nothing but minus dt by 2. And therefore, what we can write is absorb the minus in the limits and you get minus 1 to 1 half Li2 of 1 minus t square, which is a much better form than we had expected earlier, correct? Okay, so we have this form now. And again, since this is an even function around 0, we can write this as half into 2 into 0 to 1. Notice how all the properties that you have learned in high school are being used here because these are very crucial to simplify the integral into something we know, Li2 of 1 minus t square, correct? Okay, now from this step onwards, what we are going to do, okay, let's write one more step to make it clear, 0 to 1, Li2 of 1 minus t square dt, okay? Okay, so from this step onwards, what we can do is we can use the definition of dilogarithm. So Li2 of 1 minus t square was nothing, according to the definition, should be 0 to 1 minus t square ln of 1 minus x by x dx, correct? Now, what if you were to find the derivative of this term? So the derivative of this term should be equals to, firstly, derivative of this, so minus of derivative of 1 minus t square, which is minus 2t, according to Leibniz rule of differentiation under the integral sign, right? Ln of 1 minus t square and divided by 1 minus t square. So this should basically be, I think, 2t by 1 minus t square into ln of t square. That should be the derivative of dilogarithm. The reason I'm doing this is I want to do integration by parts here. And I want to take the first function as, actually first function is this one, right? Because I want this to get differentiated and this one is the second function. Okay, let's do that. So what we will get is this t into Li2 of 1 minus t square, and the limits will be from 1 to 0 minus 0 to 1. Now derivative of Li2 of 1 minus t square, we have found out that this is basically 2t by 1 minus t square into ln of t square, correct? And integration of 1 should be dt. You can find out this first term is nothing but 0, and then you can try and evaluate this one, which now is not really hard. Ln of t squared is 2 ln t. So this becomes, and we don't need to put a mod here because 0 to 1, t is always positive. Okay, so we have 4 t squared by 1 minus t squared into ln of t dt. Keep the 4 outside. Keep this 4 outside, and inside you have a minus t square, correct? Because I'm taking this minus sign inside, and then I'm adding a plus 1 and a minus 1. 1 minus t square dt. And therefore, I should be equal to 4 times 0 to 1. Do the distributive law. 1 minus t square into ln t by 1 minus t square is basically ln t dt, minus 4 times 0 to 1 ln t by 1 minus t square dt. Now, 0 to 1 ln t dt is kind of a standard integral for me, so it is basically equal to minus 1. I have done it a lot of times, but you should try and verify it. It's minus 4 minus 4 times, and now 1 upon 1 by t square. Again, the geometric series in action. What I'm going to do is this: 0 to 1 ln of t into 1 by 1 minus t square dt. And this 1 by 1 minus t square is nothing but the infinite geometric expansion of 1 plus t square plus t to the power 4 plus t to the power 6 and so on, because mod of t square is less than 1 and this is valid. So minus 4 times 0 to 1 ln of t into summation m equals to 0 to infinity t to the power 2m dt. Makes sense? Now minus 4 times, and now I'm trying to interchange the summation and the integral here, and this is valid right now, at least. 0 to 1 t to the power 2m ln of t dt. Now you can understand a general result here. So 0 to 1 x to the power a and ln x to the power b dx. This is a general result which can be proved using a very clever way, is minus 1 whole to the power b into b factorial by a plus 1 whole to the power b plus 1. This is the result. And you can try and prove it simply using the integral of 0 to 1 x to the power a dx. Do not try and do anything else. Simply try to prove it using this result itself. Let me know if you got it. Okay, so let's continue with this one. Minus 4 minus, and now we know that this here a is 2m and b is 1 according to our result. So this should be equal to m equals to 0 to infinity minus 1 to the power 1 into 1 factorial by 2m plus 1 whole to the power 1 plus 1. Okay. Now, therefore, this becomes minus 4 plus m equals to 0 to infinity 1 by 2m plus 1 whole squared. Therefore, the value of I is then summation of m equals to 0 to infinity 1 by 2m plus 1 whole square minus 4. Now, this quantity right here is the sum of the reciprocal of the squares of all positive integers. What I mean is this: 1 by 1 square, 1 by 3 square, 1 by 5 square, and so on, minus 4. But remember, okay, I think there was a 4 here, right? I forgot the 4. There was a 4 here as well. 4, 4, 4, and 4. Okay. Okay, now what we are going to do is we can write this entire thing. You can see the even integers are missing. So we can write 1 by 1 square, 1 by 2 square. We can add all the even integers and make this a sum of all the reciprocal squares of all the integers minus, well, obviously what you added. 1 by 4 square plus 1 by 6 square and so on. The reason I'm doing this is because this first sum is nothing but n equals to 1 to infinity 1 by n square, correct? And the second sum is n equals to 1 to infinity 1 by 2n whole square minus 4. This means the first sum is n equals to 1 to infinity 1 by n square as desired. And here 1 by 4 comes out because it's a constant, and you again have the same sum n equals to 1 to infinity 1 by n square minus 4. This would mean that 4 times you can take summation n equals to 1 to infinity 1 by n square common, which converges, this is a p series, and multiplied by 1 minus 1 by 4 from this, okay, minus 4. So this becomes 3 by 4, and 4 into 3 by 4 is 3. So the answer is 3 times summation n equals to 1 to infinity 1 by n square minus 4. This is the value of I. Okay, let's get back to where we were with I. So we found out that S is basically equal to I plus 4, right? Our summation was equal to I plus 4. So our required sum n equals to 1 to infinity 4 to the power n by n square into 2n cn was equal to I plus 4, where I right now we have got as 3 times n equals to 1 to infinity 1 by n square minus 4 plus 4, correct? And the minus and plus 4 cut off, and this summation has a value of pi square by 6. This is the famous Basel's problem. You can search it up around 1760s or something, and Euler wrote a solution to this, and many others have also done the same. And this can be proved in a variety of ways. I think I have done it once on my channel as well. So anyway, this summation has a value of pi square by 6, which makes our required summation evaluate to pi square by 2, which is such a simple answer for such a complicated giant. Well, if you did like the video, please let me know in the comment section. And thank you for watching. I'll bring more such content.